Is this the quiz?
But if you want a quiz, I'll give you one.
No, I was just asking.
I'll say no pretty fast. Okay, so when we talk about temperature, we're gonna have it in the US we use what degrees? Fahrenheit. So we use Fahrenheit. The rest of the world use Celsius. And in science we use Kelvin. Okay. Now, let me give you the significance of Kelvin. Number two are just, it's what they've done, what we will do. So you need to be able to go from Fahrenheit to that. And then you need to be able to change that to Celsius because that's what the world changes to that. And sometimes in science we use Celsius, but primarily we use Kelvin. Kelvin is considered to be absolute zero. From absolute zero. You know what that means? That's right. What about molecules? What do they do? What atoms? What was that? They make up everything, okay? And normally, do they move? Do they not move? There's a theory somewhere out there. You guys remember that theory? Okay, exactly that, exactly. So what's that theory called? Kinetic what? Kinetic energy is the process of movement using energy, but there's a law, right, or a theory. It's called the kinetic. First part, kinetic what? What did we talk about in this class? Talking about what was that? Well, we know it's a theory, but come on, it has theory in it. Come on now, let's see. What was that? Somebody said it. Kinetic molecular theory. That is correct. So that says what? So remind me what it says. If you mentioned it. They're always moving, right? They're always moving until you reach absolute zero. Absolute zero is the point where they stop moving completely. Things just stop moving, right? Okay. So the Kelvin scale is based upon the absolute zero. Things stop moving at negative 273.15 Celsius. Okay, so that's when things stop moving. Okay, so that's how we base it upon that scale. Okay, so the Kelvin scale is based upon absolute zero, and that basically says that things stop moving on that. And so that's why we base our Celsius to Kelvin. That's why we use it that way. That's why we use 273.15. Okay. So let's say water boils. Water boils at what degrees Celsius? Does anybody remember? 100 degrees Celsius. How much does water boil at Fahrenheit. Guess what you're gonna do? You're gonna plug into this equation. 212, right? So if we plug it into this equation, it should add up to 212. So we put 100 in here. Multiply that by 9/5 plus 32. That equals 212. 90 plus 30. Sorry, 1 8 plus 212. So if water freezes at 0 degrees Celsius, what is it going to be at Fahrenheit? It's going to be 32. 0 here. What times 9/5? Okay, do you see how to use the equation?
Yeah.
Okay, so you need to be able to convert from Celsius to Fahrenheit, or Fahrenheit to Kelvin. There's one more, it's called Rankine. Rankine is based upon absolute zero, but that's for Fahrenheit. In the US engineers only use that, so I'm not gonna make you guys do it, because most of you guys aren't gonna be engineers. Okay? Questions? Concerns? Cash? Kool-Aid? Okay, so let's see if we can test this out. Okay, everybody got it down. Took a picture already? So if you look on your handout, and there's an Army sheet. There's Army on it. If you look at that last column, the very, very top, it actually has the equation. For everything except the Kelvin, right? So you guys may want to add that on there. Okay. Are you next to people that you like? Groups of 4 roughly. If you're not in groups of 4, please try to get in groups of 4-ish. Okay, everybody ready? So remember, I told you about competition. This is what we're going to do. Okay, so what I'd like you guys to do is to finish the table. Team that finishes first will get a point of extra credit add on to their score. Yeah, let me correct. Finish it first and it's correct.
No, they're just plugging it in.
Hey,
And then finding other.
Yeah. Yes.
Yes. Sure. Actually, tell Destiny that it is on the syllabus. She just clicks on it. And she'll open it. You got it?
Oh, okay.
Yeah.
No, yeah, that's.
So what would the? For each line.
Good morning.
You want us to bring to you to check it?
Yep. Got it. Okay, who's bringing it up? Who's bringing it up?
Oh, you know what? I said this. That's just this. You gotta have something. For real.
Yes. Numbers on there?
What are they doing?
Say pigs, say pigs, everybody got say pigs? I'll give you that cool picture of say pigs.
Wait, that's not there. Yeah, there. Oh, yeah. That's all. Oh, I switched it.
Let me give you guys a little bit of a hand, just a little bit. Okay? It's gonna be a little bit of a hand. Okay, so. All right.
Okay, so I guess the
Okay, so if we're using this equation, these are exact numbers, right? So they're kind of like saying 5.0000000000. But you don't take those numbers into consideration for significance. However, this here is not necessarily considered exact, right? just kind of leave it. It should be considered an exact number, so. Right, so really, it's sort of dependent on this number. Okay. So this number kind of helps us determine our slope. Okay, except this in this case, for us. Okay, does that help a little bit? I'm just saying, you good? Comfortable? Confident? Okay. Were you listening on the way in?
Yeah.
Yeah, just for reference, if you guys are looking for the link is always gonna be on the syllabus. It's that selection link. It's gonna be that same one. If you just click on it, it should take you guys there. So, in the future.
Probably be late.
What was that? Yeah, you saw I was gonna be late.
Yeah.
No, I was already
Late. I woke up like at 8.
The first person that gets it.
Yeah, we're trying to.
You guys want to add it on to your extra credit to your final or to your your
1 point for
team?
the final. I know.
Yeah. You want to add it on to the final? Okay. Can you-
Just relax for a second.
One, you gotta pick.
kidding.
Sign. One, the other's just-
Oh, Harrison, fix it.
You guys fix it. Well, this one is okay. I'll put okay. Otherwise okay.
Oh, no, not that. I think I fixed it. Let's just sit there.
Okay.
I did have one. I don't think you can actually.
Okay, the one that says okay is okay. Close.
Oh, so then we're. It was 39. Yeah, but she was.
Okay, so what I'm gonna do is,
She was 39.
we're looking for time. You guys are a group?
Yes.
Okay, right here, this is group, this is group. So you can consult with the group next to you, see if you guys can get anything back. And then both of your groups will get points if you guys get it correct. So use that opportunity to consult. I'm gonna give you guys a couple more minutes. And then otherwise, nobody gets points.
Oh, Jesus. No, she's right now. So obviously we're wrong. That was wrong. They got 40 wrong.
So this one's right for you guys?
Oh, so they got that one right. But for the 40.
Let me tell you, you're really close. Right, so you're missing one, right? You're really close.
Oh.
I know which other ones you have wrong.
We got that one wrong. Two items.
Think about how you broke things down. Obviously, you know it's okay.
Okay, you ready?
Yeah.
Yes.
But we're.
This one's okay.
The 39.
Okay, you're down to one. Really, really close.
Okay.
Really close. What do you guys think?
Okay, can you give us
I'm giving you a hint.
a?
You're obviously you're missing one, and it has something to do with sig figs.
So we're just missing one.
Oh, I got it. I got it.
Still. But you did. That's really wrong. Yeah. You got it?
Is this one?
Okay. Are you saying this here? That there, no.
Oh, I don't know if we showed you this one already.
You
We were
showed me
closer the
one-
other
yeah,
way.
you were closer the other way, yeah.
Is this still?
That's still wrong. You gotta think about sig pigs. Think about sig
Wait,
pigs.
Dr. Henry. Okay, so you're talking about sig pigs.
Mhm.
Cause it's saying you got one, two, three, four.
It's not 4. No, you guys are closer to the answer that you guys have there. I mean, you're really, really close. But you gotta think about how you have it written. That's all I'm saying. How you have it written.
Okay, what did you guys get? Oh, this is the one we're showing.
Yeah.
You said that was
For this
one.
one. Yeah, we put it on.
Yeah.
No, I'm not saying that you're closer to that number.
Oh, this one.
Yeah, we went all the
I'm
way.
saying that
we
you
did
just gotta think about how you have it written.
Oh, it's gonna be 40.0.
Yeah, we already got
Is it, wait, not, wait, think about what you wrote. Now say, think about what you just said.
No, I'm thinking is it this?
And is that, has that there?
No, yeah, that's it.
That, okay, so then yes, that is
Yeah,
correct.
that is correct.
Okay, so
I'll show you.
Wait, so what did you get right on it?
So,
Yeah.
gotta put the point.
Yes.
No, you gotta put, well, it should be 40 point.
So does that mean
Now you're just getting rid of things.
it's 40?
Okay, so let's talk. So close, good job, guys. Good job. So is that decimal point, right? Doesn't that mean that you had that so significant figures to get to that lining up, right? So because you had to line it up, you have to make sure that it ended at that significant figure, right? Okay. So, and if you just wrote 40, that was only one sig fig. You need 2 because it needed to line up, right? So that was talking about. Let me put your answers up there. So share with the class. Okay, so those are things that you have to think about. I mean, they're minor things, right? Minor things, but I like sig figs. I'm obsessed with sig figs. I'm obsessed with sig figs, right? They seem like, because when you start working, and you guys got to realize, you're gonna start working with big cohorts, because a lot of times your hospital will be doing studies, and so you gotta have to keep track of data from, you know, patients, this doctor, and that doctor, and that doctor, and not all doctors are created equal. Right, so, and guess who's gonna be keeping track of the data? Yeah, you. Okay, you guys are really close. So it was just sig figs. Your numbers are right, but you want to get those sig figs right, right? Okay. Okay, good. So you guys are feeling comfortable with temperature overall, though?
Yes.
Okay,
Yeah.
good. Okay, everybody got the answers? Feeling good? Let me give you guys your points.
Thanks.
I will forget. So, as I said, I like competitions. We'll have another one here soon, so get ready. Okay, so let's talk about density. Can I erase this? Everybody got this down? Let me erase it. Okay.
That was like this, like I was like. No, you cannot get out of it. Like, I'm very. It just goes. And then the next one should be the not really have one fairly like covered some. Here's the next one. Yeah. Yeah. No, we didn't. Oh, she said it?
So we talked about proportionality already, right?
That one.
Okay. So when we talk about proportionality, we often will be talking about things that are directly proportional to each other. We kind of talked about that briefly. So we talked about density. I'm giving you an example, density. So density is a constant. Not check 5. We're almost there. So we're going to use big D for density. And that's going to equal mass over volume, right? Okay, so we said that when things go up at the same time, they're considered to be directly proportional, right? So the density is going to go up, right, if the mass goes up. We know that the density is going to be constant. It's always going to be the same value for certain things. And I'll show you an example of that in a second. So we don't need to worry about this, right? So this guy's going to be totally constant. Okay, now the volume though isn't going to be constant. It's going to be constantly moving, right? So if the mass goes up, because that density is held constant, let's just make that density a constant. Change our equation a little bit. Okay, so if we move the volume on the other side, we have mass being proportional to volume. And that D represents the density. Okay, so if my volume goes up, then my mass is going to have to go up to counteract it. They're going to be directly proportional to each other. Okay, and so that's basically what this is saying. So as one goes up, the other one has to go up. Okay, so for instance, we know the density of water is 1 gram per milliliter. Water. Or roughly. You guys calculated that, right? 1 gram. Right. Struggling here today. Okay, so if I have 100 grams of water, what must be the volume of that water? It has to be 100 mL. If I have 1,000 grams of water, what must be the volume? If I have 5,000 grams of water, what must be the volume? 5,000. So this shows us that it's directly proportional. As we increase the mass, our volume had to increase proportionally. Does that make sense? 100 to 1,000. 100. 100. This also had to increase. Right? From 1,000 to 5,000, they had to increase. Right? So it's directly proportional. Okay, so those two are directly proportional to each other. Okay, so say we have work. Work is defined as P times V. P represents pressure, V represents volume. And this can be under perfect conditions. They can be set up as a constant. Okay, so if that constant, again, let's assume that constant is going to be 1. For work. So constant is going to be equal to 1. If P, the pressure, is going to be 50 ATMs, then the volume has to be what? For it to equal to what? Has to be 50? Yeah.
Right?
50? So 50 times 50 equals 1?
No, that's equal 1, you said?
Has to equal 1. Yeah, because we're saying equals that constant is 1 atmosphere per meter. I mean, 1 atmosphere per meter.
And divide it?
I can divide it. So then what is 50 divided? You said 50? 1 over 50. Okay, this is what you guys are saying. 1 over 50, right? So that's 150 liters. Okay, so that would be the volume. Okay, so if the atmosphere is 100 ATM, then it has to be what? The volume has to be what?
1 over
100. So is that getting bigger or is that getting smaller for the volume? It's getting smaller, right? So as I go up in pressure, my volume is going
100.
down. So that would be indirectly proportional. Or you'll also see inversely proportional. Okay, so you'll see it written both ways, indirectly or inversely proportional, where density is directly proportional. Okay, do you guys see the difference between the two? This is the case of density. This is the case of pressure times flow. Okay. Okay. So you'll come across, and I always have a question on the exam. Look at the question, right? If the two factors, one thing is said to be constant, and the other two things are, in the case of directly proportional, they're both on the same side, one over the other, right? Then they're going to be directly proportional. Right? If they're next to each other, like P times V here, they're going to be indirectly proportional. Okay? Always, you're going to always get a problem like that. It may not necessarily be work, or it may not necessarily be density. It may be energy. Right? So pay attention to that. Okay, can I erase this? Okay, so we know that density is going to be equal mass over volume. Usually density is represented in grams per milliliters, or it's grams per cubic centimeters, right? So you know that a cubic centimeter is the same thing as 1 milliliter. Okay, now when we talk about density of gases, we do it a little bit differently, but for the most part, when we talk about liquids or solids, we're going to use grams per million. Okay, now the thing is about density, it's going to be dependent on temperature. Why do you think it's dependent on temperature? So you said temperature can increase weight or decrease it. Why?
Because it, sure, because it freezes. And they can hear it freezing.
So will it weigh more if it's freezing, or will it weigh less if it's freezing? Sure. You go with your first answer. Your first answer was correct, but why? Why would it weigh more?
Why would it weigh more?
Why would it weigh more?
I'm just assuming that you're freezing everything around it as well.
Well, we don't care about everything around it. We care about what we're talking about. Say we're
But you
talking
said
about
everything
iron
is-
or steel.
You said everything's at a touch, so when it's not at a touch, it's stuff where it's at. So
What do you mean by it? What now? What is your definition of? Because think about what you're saying. Because I didn't say that everything is a constant. I said for density, density is a constant, right? So density is held the same at a given temperature, but density is dependent on temperature.
also, yeah. Okay.
Okay. So it's but why? But why is that the case? So you say as the temperature goes up, the mass goes up. That isn't necessarily, that isn't true. How tight they're packed together. So wait, that goes back with something that we just talked about. What was it that we just talked about? Well, obviously, we talked about density. Come on, now, beyond that, before that. What was that? Say it again. Kinetic molecular theory, right? Because you're not moving. If you're packed, have you guys been to a club? Been to a club, right? So if you're in a club and it's really packed, or a party, I know you've been to a party, right? But I know you've been to a party. So if it's a really packed party, can you move?
Let's just say before, no.
No, you can't, right? So when we think about solids, you can't move. And so you're really packed together, right? Now we know that if you're not packed, you can move, right? So the more you move, the less you're actually going to weigh, right? You know, and so because all those molecules are technically moving, it should technically weigh less, right? Technically. All right, some exceptions, right? Talk about that here in a second. Okay, so, but when it's a gas is all over the place, right? And so in that context, technically it should be the same amount of weight overall, but it's all over the place. It's going to weigh less. The density is going to be less, right? In the case, okay? So that density is going to be less in the context of a gas than what it's going to be in a liquid, than what it's going to be in a solid, in most cases, except for water. Okay? Water is an exception because we know that ice floats on water, right? Okay, so this is that example, ice floating on water. Okay, so if we have ice here, all nice solid, it's nicely organized. Now the thing is that it has these little spaces. Since it's so nicely organized, it has that space. It's not completely packed like we have in the case of water, right? So because it has that little space in between, that nice organized space, it causes ice to be less than water. It will actually float, right? So then ice floats on water. That's why an iceberg floats on the ocean. Okay? And so that means it doesn't freeze everything below it. So that means that the fish below it stay alive. They don't get frozen to death, right? Because of that. Okay, so this is just basically showing you ice floats on water. Now, if I put a solid thing of ethanol, well, ethanol doesn't form that nice little structure, those little gaps. So it actually will sink in ethanol. So this is ethanol liquid. This is the ethanol solid. And it sinks to the very bottom. It doesn't float. Okay, and that's because the density of ethanol as a solid is more that than it is of the liquid. Or ice is different. Okay, here are some examples. Helium gas, really low density. Air, very, very low density, right? Helium gas, we know it floats on air. Why do you think it floats in air? It's less dense than air, right? So that's why helium balloons will float off, because it's less dense. Okay. Lumber, you guys see lumber float on water? Why do you think it floats on water? Less than water. Why? That's the reason why boats float, right? Because they're less dense. Okay, water, density of water, density of glass, density of aluminum, density of iron, density of copper, density of silver, density of lead. You know that you've heard of people getting lead weights tied to them and thrown in the ocean and stuff like that to keep them down. Well, that's because they're more dense than those people that they tied them to, right? Okay. Huh? You missed the conversation, right? You tap out for a minute, you missed the whole thing about people being thrown in the ocean, right?
No, I was there.
Oh, you were there. You were there when they were throwing people in the ocean? Okay. So we know the person that's responsible for that, huh? Okay. Okay, so I want you guys to determine the density of methanol. Okay, so we know density is what again?
Mass over volume.
Mass over water. Okay, so what is the mass?
Oh, mass is
39.39.
You're just gonna give me the answer, huh? Okay, and we're dividing it by the volume. What is the volume? Okay. That's milliliters, so my answer is 0.7918.
Let's take out the first 8.
Take out 7.
Yeah.
Okay, how many sig figs? 4. 4, I guess 4. Okay. And my units?
Gram.
Piece of cake?
You don't like that.
Okay. They're all kind of like that. You may have to do a little extra work to get there. But... Okay, so the density of a certain machine oil is 0.910 grams per milliliter. Find the volume occupied by 196 grams of that oil. How would I do this?
It's supposed to be showing your screen.
What was that?
This is supposed to be showing up there.
Is it not showing?
Oh, no. Still recovering.
How many do I just?
196 grams divided by 0.910. There's
Okay.
2.53. Oh no, 215.38.
Okay, so you're saying 196 grams divided by 0.910 grams per milliliter.
Yeah.
Okay. So grams are gonna cancel out. And just milliliters.
Yeah.
What do you guys get?
So I got 218.38.
215.38.
Yeah.
Okay, how many sig figs should I have?
Take away all the negatives.
I should have 3 sig figs. Okay, so then my final answer should be. See,
Yeah. Milliliters.
15 milliliters, that's right. Okay. Questions? Piece of cake? Okay. So now we're gonna go to chapter 5. You guys want to take your break now, or do you guys want to wait to take your break?
Take it at 10.
Want to take it at 10? You like it at 10?
Right in the half working.
Okay, sounds good.
You're on your catfishing with your profile pic.
What was that?
You're on your catfishing with your profile
That's
pic.
right, you know. I need to get my next girlfriend, you know. Sure, my current girlfriend will like that. So have you guys learned anything that's undoable? All piece of cake, right? It's a matter if you put in the time.
Learn.
You have to convince yourself to learn.
No, I had to make myself.
Maybe.
Even if it was hard, I had to. In my brain. It looks like. Like.
Okay. Okay, so Dalton is a scientist that basically. Okay, so Dalton is a scientist that basically came up with the theory, or the atomic theory, right? And he basically said that atoms are indivisible. You know what indivisible means? Why don't you get distinguished? Oh, you can't break them up, right? You can't break them up. Atoms can't be broken up. That's the small thing, right? Each atom is made up of particles. I mean, each element is made up of particles, all atoms. That was the first thing that he said. And then he said that all atoms of one element are exactly identical. They're perfectly identical, right? And then he said that atoms of one element can be combined with atoms of another element to make a compound, right? Which we already kind of know about that. We already talked about that. Now, I want you guys to think about this, right? Think about this theory. And what is a theory, by the way? Okay.
That can still be.
Well, that's a hypothesis, right? A theory.
It's just not a fact.
Okay, so it's not necessarily a fact, right? But it's something that parts of it can be proven or part of it is not proven. So this is where he started at, right? Now, I want you guys to think about it. Now, he wasn't quite right. I'll let you know that now. And I want you to think about why he wasn't quite right, okay? Anybody want to give a guess immediately? And then we'll go through the lecture. Why wasn't he quite right?
Because the atoms had to, like, from the same particle, they had the same element, they had the same different weights.
They get out different ways.
And
Oh.
they were separate.
Okay, good. Okay, and you said, and they were separate. Okay, so it wasn't indivisible, and you could have from the same element, that's the carbon, it could have different weights of carbon. Okay, so we'll talk about that. Somebody's reading ahead or remember chemistry from before. Okay, so this just basically says exactly the same thing he said. First thing that he said was atoms are made up of elements, and all elements are elements. All atoms of a given element are elements. Well, we know that that's not the case because we've been informed, and I'll show you why. Atoms can be created or destroyed. Well, we kind of know that you can't create or destroy them, right? But they can be separated, right? And we'll talk about that here in a second, right? Or parts of that atom. All atoms of a given element have the same properties as mass. And we know that that isn't true because we know about isotopes. You guys have read ahead, and we're going to be talking about isotopes. So atoms of different elements have different masses. Okay, and we know that they're going to have different properties, right? But they could end up having the same mass. So we'll talk about that here in a second. Two, atoms of different elements may be combined in different small whole number ratios. Yeah, whole number ratios to form compounds, and that's going to be kind of important because we need those whole number ratios. Okay, so the law of multiple proportions, that basically says that we can combine things in different proportions, right? So for instance, we have carbon monoxide, one carbon, one oxygen, and we have carbon dioxide, one carbon, two oxygens, right? Aren't they different? Yeah. They're not exactly the same thing, right? They don't behave the same way. They have different properties associated. For instance, carbon monoxide, although if we only had carbon monoxide in the room, if we only had carbon dioxide in the room, it would kill us because we need oxygen to breathe, right? And we breathe that carbon dioxide. But if there's oxygen in the room, we'll be okay, right? As long as there's some oxygen in the room, we're fine. If we have carbon monoxide in the room, it gets to a certain point, it'll actually kill us, even if there's oxygen in the room, right? Have you guys heard of carbon monoxide poisoning? Right? Gas pipe, tailpipes, stuff like that, right? So even though that there's oxygen present, just having that carbon monoxide will kill you. Well, that's because those two have two different properties, right? Carbon dioxide and carbon monoxide, they have different properties. They behave differently when they react with our lungs. Right? Okay, so they're not the same thing. So having a ratio of 1:1 is going to be different than having a ratio of 1:2. Okay, so law of multiple proportions basically says that these two things are different, right? But they have that whole number. You notice 1:1, 1:2. You don't have 1 and a half, right? Because you can't have a half of an atom. Okay. So there are components. The atom can be broken down into 3 parts. There's the electron. The electron is negative. Now, I would normally give you guys the history. We'll go over history for like a whole day. Don't worry about the history. All you need to know is J.J. Thomson was the guy who discovered it, right? And that it's negatively charged. The other thing that you need to know is that an electron is so light. So for instance, I weigh 220 pounds, right? If I put a speck of dust on my shoulder, would my weight change if I stepped on a scale? Speck of dust, just a drop of dust. Right? It's not going to change at all, right? I'm still going to weigh 220 pounds, right? So the electron is so light in the atom that it doesn't affect the weight of the atom. It has no effect on the mass or the weight. Okay? So the atomic weight does not take into consideration the electron because it's so light. What was that? What did I just said?
Electron is so light.
Okay, so we don't take any consideration at all for the weight. So the electron is also negatively charged. It has a negative charge associated with it, okay? So we have electrons. The other thing that we have are protons. So protons are positively charged. Protons affect the weight. And the last one are neutrons. Neutrons are neutrally charged. What do I mean by neutral? They don't have a charge. And they also affect it. Okay, so the atomic mass of an atom is going to be made up of the number of protons plus the number of neutrons. Okay. So, or we'll say the atomic weight will be made up of the number of protons plus the number of neutrons. So when they were thinking about mass and how to define mass and everything like that, it was actually based upon that proton. Okay? How much that proton weighs, right? And so they say, okay, so this proton weighs about this much based upon our weight system, right? And so that kind of defined everything, okay? So then they said, okay, relative to a proton weighs about the same thing as a neutron, right? And then they said the electron hardly weighs anything. Well, they didn't say. They determined it. It's about 5,316 times less than the weight of a proton, right? And so really, it's nothing compared to a proton. Okay. So when we think about the mass, the atomic mass on your periodic table is just a combination of your protons plus your neutrons. Okay. So okay, everybody get that down. That's where I'm going to erase all my writing. Okay, so here we have hydrogen. Okay, you guys all see hydrogen there? Okay, if we take a look at the very top number, this is called our atomic number. The atomic number represents the number of protons. Okay, the atomic number defines the element. Okay, now what do I mean by that? Anybody want to take a guess what I mean by that?
What did you say again?
The atomic number defines the element. Anybody want to take a guess what I mean?
That's like a signature, like a thing. We identify it.
That's right. That's how I identify it, right? So the atomic number tells me what element it is. So if I tell you it's atomic number 21. What element am I talking about? That's right. If I say it's atomic number 15, what element am I talking about? Okay. So that tells me what element. It also tells me what? Wait, somebody, everybody say it under their breath. You gotta say it loud so I can hear it. Number of protons, that's right. It tells me the number of protons. Okay, so that is shown right up here. Okay, so that's the atomic number. Okay, this here, down here, this is called the atomic mass. So what did I say the atomic mass was? Okay, now it's the number of protons plus the number of neutrons. But you're going to tell me, right? You're going to say this to me, and you're going to think about it, right? 1.008. That 0.008, can you have 0.008 of something?
No.
Let's say, for instance, we're talking about iodine. Can I have 0.008 of iodine? Cut a little bit of iodine off? No, it would probably not be a good idea, right? So when we see the atomic mass on the periodic table is just the sum of different isotopes. Shit, that word, isotope. Talk about that. Huh? Just think about it. Okay, isotope. Iso means the same. Isothermic, isotonic, it means the same. Iso, ISO, it means the same. Okay, isotope means same of protons, but different number of neutrons. Okay, so if I have the same number of protons, but different number of neutrons for two atoms, right? Two, we'll say hydrogen atoms. What does that tell me about the weight of those hydrogen atoms? They're going to be different. Okay, so we can also say it's the same number of protons, but different mass, right? And you'll see it written both ways. Right? Two ways. This. Okay, so an isotope of carbon is going to be one carbon with one, and one carbon with none. So when we talk about the atomic mass that's shown on the periodic table, in nature, what happens is that we have isotopes that are naturally occurring, meaning that they're not man-made. By nature, they exist, right? So for instance, hydrogen has three isotopes. One is called tritium, one is called deuterium, and the one that we normally talk about is just a hydrogen. What was that? You should know. You'll come across them, particularly if you guys are going to do any radiology or anything like that, or patients are going to go through any type of it. They'll often need deuterium for some of the studies that they do. Okay. So you should be familiar with it. Okay. So those are three ones that occur naturally in nature. Now, the one that's most abundant, based upon the mass here, is going to be the one that weighs one, right? Not the one. Deuterium weighs 2, and tritium weighs 3. Okay, tritium, TR 3, deuterium 2, and then we have, I think it's called, its real name is like proterium, meaning that it just has a proton. Okay. So if we look at this mass, we're going to have to take the estimate, right? So we want to get it to the number that it is closest to. In this case, this is really close to the whole number of what? 1. Okay, so if it weighs 1, how many neutrons must it have?
One.
Are you sure?
Well, no, it could be different.
Are you sure? If it weighs 1, how many neutrons must it have? Okay, atomic mass again is what?
No, protons.
Number of protons plus neutrons. What did we say about having a half? Can I cut you in half? Would you be okay if I cut you in half?
It's gonna be one, right?
No.
Oh, never, I'll take it.
Okay, first off, let's talk about it, right? So you guys just told me, we're gonna write this on the board. So we said that the atomic mass
Number of protons.
equals protons plus neutrons. Okay. So now the atomic number for hydrogen is what? 1. What does that tell me? It has 1 proton. Now, if you just told me 1 equals, it has no neutrons, right? But you gotta speak up. If you talk under your breath, I can't, I'm not a mind reader. You gotta talk. You guys see that? Right? So, because it can't be 1, we know it can't be 1, it has to be 0, right? So we know that the hydrogen atom, right? If we're talking about the one that's most abundant, has only 1 proton. How many neutrons? 0 neutrons. Okay, so we're talking about,
How do you know that it has 0?
because what is the atomic mass? How much does it weigh?
One.
It weighs 1, right? Tell me. 1 minus 1,
Oh, yeah, it's 0.
that's 0, right? So then that's how we know it's 0.
So if it was.
So
2,
for instance, if we're talking about deuterium, right? Which is, okay, let me explain this. So this here represents what we call the mass number, or the atomic mass. This here represents the atomic number. This is the way that we would write an isotope. Okay, so this is how we would write deuterium. Okay, so in this case, okay, so in this case, this isotope weighs how much?
1. 2 minus 1, right?
How much does it weigh?
2.
It weighs 2, right? Because that's the mass of it. That's its atomic mass. Okay, so it weighs 2. Okay, how many protons does hydrogen have?
1.
1. So then how many neutrons must hydrogen have?
1.
This deuterium has 1. Do you guys get that?
How do you know it only has 1 proton?
Because it's the proton.
Okay, what defines the element?
The atomic number.
What was it? The atomic number, right? That tells me that it's hydrogen, right?
Yeah.
So we know that this number down here defines the element in this case. On our periodic table, it's the number at the very top, right here. This represents the atomic number. Hydrogen, anytime that we're talking about hydrogen, we're saying hydrogen, right? Hydrogen is going to be 1. That's its atomic number. It's number 1. It only has how many what? Protons. It has 1 proton, right? If I was talking about carbon, what is the atomic number for carbon? 6. So if I want to talk about carbon, carbon is going to be 6. So if I write carbon,
Oh, but it's always gonna be minus 1.
what do you mean by is it always going to be minus?
Never mind.
Will be the mass minus the number of protons.
Could you have 0 proton
Okay,
and
I see.
just 1 neutron?
You can never have 0 protons. You don't have, okay, wait, let me make a correction, right? You can have a neutron, right, on its own, but you can't have an atom that has 0 protons. All atoms have to have a proton. And that atom has to be defined by a proton. Hydrogen is always going to have 1 proton. Carbon is always going to have 6 protons.
You have multiple protons? Like, how do you know? So say for instance, you have the atomic mass is 6. How do you know like you exactly have like 3 protons and 3 neutrons? I don't get it.
So he's getting into it.
That's the point, right? Because if it has, okay, let's talk about that.
Yeah.
You said it has 3 protons.
Mhm.
Atomic number means how many, what would be the atomic number for that element?
It's gonna be
Look at your periodic
the
table.
same number of.
Look at your periodic table. 'Cause I want numbers here.
You talking about for carbon?
No, I'm not talking about carbon. You said 3 protons. You said specifically,
Oh.
it has 3 protons.
Oh, okay.
You get it?
Yeah.
Okay, so your periodic table tells us about that element. What element has 3 protons? Lithium. So that means that we're talking about lithium. As soon as you say 3 protons, we know everybody in this class knows who we're talking about, right? That's kind of like when I say Magdalena, right? We know we're talking about you, right? Because that represents you. That's who you are, right? And then we start talking about description of you, right? And so that's what we're doing with this. These are like descriptions of how much you weigh, you know, your color, you know, those are characteristics. Yes.
Sorry, don't get upset.
I'm sorry.
So if we were to talk about lithium, so then you'll do the 3 minus the 6 or whatever, the 6 or whatever.
Okay, so let's do lithium as an example, then we'll do carbon, we'll go back to carbon, right? So lithium, if we're talking about lithium on the periodic table. The symbol for lithium is
Li.
Li. Okay, how many protons does lithium have?
3.
It has 3. So we write that down here. That tells me that it has 3. We're talking about it has 3 protons. That just reminds me that there's 3. Okay, how much does lithium weigh?
6 point.
So it says 6.94.
So just 6.
No, look at that number. 9. Is 9 greater than 5? We round up. So this guy is closer to 7, right? Okay, you want me to go back over this,
No,
right?
we get-
Because you
no,
had that
no.
look. 6.94, right? So because we can only have whole numbers, right? Can I cut you in half? Would you be okay if I cut you in half? I cut off your hand. What if I just cut off your hand? You okay? No.
Why don't they just put 7 on there? instead of
Because it
6.94?
it's on the periodic table, it represents isotopes. It's multiple isotopes. One of them weighs 7, one of them weighs 6. The one that's 7 is the most abundant. Right? So for instance, how many people are in your family? No, just curious. How many
9.
people? Yeah, 9 people in your family.
Yeah.
That's a big family, right?
Yeah.
Okay, so you have 9 people in your family. Okay, now how many cousins do you got?
3.
You got 3 cousins?
Yeah.
How many people are in their family?
Just make them a
In
number.
their family.
Okay, 5.
Okay, we'll say 5. So you got
Yeah.
5 in one cousin, and we'll say 5 in the other,
Yeah.
just for the help, right? Okay, so your family is the most abundant. There's 9 of you guys. Cousin number 1 has 5. 5, right? So when we're talking about isotopes, your family is like one of the isotopes, right? The other isotopes is here, has 5, and this one has 5. If we added them all together, that represents your whole family, right? Okay, so, and then if I say, okay, if we want to just look at that fraction of it, that's just your family, you guys have the most abundant. And so we just take that average, and it would be closer to your family because you're the one that's most abundant. Okay, so when we talk about isotopes, right? Isotopes are representing each of the different weights, right? Your family represents one weight. Your cousin family represents the other weight. Your other cousin family represents the other weight. Okay, does that make sense? We'll get into it more detail. Don't worry about it, right? So now the point is that what we see on the periodic table, the reason why they don't give us a whole number is because they're taking into consideration all families
Okay.
that are lithium, right?
Okay.
Okay, do you guys get that? So we're taking into consideration all the families that are there. There's lithium that weighs this much, there's lithium that weighs this much, there's lithium that weighs this much. The one that's most abundant, because it's so close to 7, is 7. That's the one that's going to be the most abundant. It's going to be like 90%, right? Where all of the other lithiums are going to be less than. Okay. And so that's the reason why it's close to 7.
Yeah, makes sense.
Okay, it makes it'll make more sense once we get to that part of it. But you guys are just getting a little bit pieces and pieces here. Okay. Okay, so if we're talking about lithium, we know that it weighs, its mass number is 7. Okay, and since its mass number is 7, that means that it weighs 7. Okay, so the number of protons, let me say P. How many protons does lithium have? 3. So if we want to calculate the number of neutrons, we're going to represent this big N here. Then we just subtract 7 minus 3. And that's going to equal our number of neutrons. Okay, so if we're talking about one of the isotopes of lithium, let's say we're talking about lithium 5. Okay, so if we're talking about lithium 5, how many neutrons does lithium 5 have? Right, because we know that 5 minus 3. Okay, so the number of neutrons it would have. Okay, so you guys good there? Okay, so here's the next thing that I want to say. Now we're talking about an element, right? These are all called elements or atoms, right? An atom is neutral. Things that are on the periodic table are neutral charge. Okay, now when we're talking about charges, and we said that protons weigh how much? I mean, the charge of protons were what? Positive, right? Proton positive. Okay, so protons are positive. Electrons are negative. So if I told you that they're neutrally charged, what does that mean? It's either positive or negative. So, but I told you that every atom is defined by the number of protons that they have. Okay, so hydrogen must have how many protons? How many electrons must hydrogen have? How many? 1. Why? They cancel out that positive, right? So we know that hydrogen has to have 1 proton and 1 electron if it's neutrally charged. Okay? So hydrogen 1 has how many protons? How many electrons? And how many neutrons?
0.
Okay. Tritium has how many protons? How many electrons?
1.
And how many neutrons?
2.
Okay, piece of cake, everybody got it? Okay, you guys give me that look over there. Oh, let me put this on the, yeah, you guys can't see. Just gotta tell me. Not because I'm blind, it's just your butt's too big. I can't see through your butt. Yeah.
Can you go through it again on how to find electrons?
Okay, so when we talk about electrons, the electrons have to equal the number of protons if it's neutrally charged. It has to add up to 0, right? So positive and negative, right? So if it was a negative, right? If it was all negative, then we'd have a negative charge. If it's all positive, we have a positive charge. We want it to be 0. When we're talking about atoms, they're neutrally charged. They have a 0 charge associated.
Oh, okay.
Does that make sense?
Right, yes.
Okay, so it has to add up to 0. Okay, so let's start talking about carbon. Carbon. So we talk about carbon 12. Okay, carbon 12. How many protons is carbon? Okay, carbon has 6 protons, right? Because that upper part is the mass, right? Remember that upper number is the mass, okay? How many electrons must carbon have? How many neutrons must carbon have?
0, right?
It weighs 12, right? Remember, the weight is going to be its neutrons plus its protons. If it weighs 12, it has to have 6 neutrons. Does that make sense? Okay, so if I have carbon 14, I'm going to write this up here. Okay, how many protons?
6.
How many neutrons?
No, wait.
So we know it's 14 minus 6,
The neutrons.
8.
Oh, okay.
Okay, how many electrons? Yes, you guys are you're already giving them a number of electrons, right? Okay, okay. Questions? Think you got it?
Yeah.
Feeling comfortable? Okay, we're gonna test this out. What was that? We haven't got there yet. Gotta move the board along. Okay, so I'm gonna erase this. Everybody got this written down. Okay, so I want you to tell me the periodic table, and then I want you to write it as a nice. Okay. Let's see, let's do. Tell me about element that has an atomic number, about these atomic numbers. 4, 62, and 90. I want you to tell me the number of protons, the number of neutrons, and the number of electrons for those elements that are atomic numbers 44, 62, and 92.
Yeah, I just want you to find those 44, 62, and 19.
Advanced with Guillermo. So we had good,
Woke up, put it on. I didn't have time to do my hair.
Oh.
This one 45.
Come on, it's a little learning process, it's okay. Again, you want to be wrong today, so you're not wrong on Sunday, right?
Yeah.
So I'm guessing it's 662.
Not too hard, don't you?
Yeah, I think I was just overthinking that.
Yeah, and you see those numbers everywhere, you're just like.
Yeah, I just didn't understand like the first time. Yeah. like, yeah. Because there's no.
Because I was saying half of whatever. So I know that. So I was saying it's 6 plus 60, but like, so it's like. I know, but 62 plus what is equal to 150.
Okay, guys, ready? Okay, so let's start with top number 40. So what is the symbol?
Are you?
Okay, so it's mass number,
102. Oh no, 101.
it's atomic number. Okay, number of protons. Number of electrons. Number of neutrons. And how did you get that?
Subtract the 101.
I was subtracted by that number. Okay. What is the symbol for atomic number 62?
SM.
It's mass number.
150.
It's atomic number.
62.
Number of protons.
62.
Electrons.
62.
Neutrons. Okay. The symbol for atomic number 92. It's mass number.
238.
238. Number of protons.
92.
Number of neutrons. Number of electrons.
92.
Okay. Not too hard. Feeling confident? Good. Let's see what time is it. Is it 10? Okay. So let's go ahead and take a 15-minute break and you guys come back. Let's finish the next part of it. Yeah, that look. Ask it now. Ask it now so it's not gonna hurt you later. One part? That's the mass. It's not necessarily the one here. That's just an isotope, a specific isotope.
Oh, okay.
Yeah.
Oh, wait. Yeah. Wait, but for carbon, what's the mass of 12?
That's if we're getting it from the periodic table. So what's really, so this number here is a combination of this 12.011. It's a combination of different isotopes of carbon, right? So there's one that's carbon 14, there's one that's carbon 13, and there's one that's carbon 12. The one that's most abundant, the one that we have the most of is carbon 12. That's the one that's normally that we see in nature. But occasionally we'll see the others. I'm saying if we're looking specifically at carbon 14.
Oh, okay. But so say this was on an exam though, we would put, and we had to fill
No,
it
it depends on what's given to you. If I say I want carbon 14,
Right.
you want to give me the information about carbon 14. But if I say carbon, use
We're
your
gonna
periodic
put
table, you're going to use this.
Well,
Yeah.
okay,
Does that make sense?
Yeah.
I know that's the part that gets a little confusing, and that's, we'll get into it in more detail. And then once we get to it, you're like, oh,
yeah, because I got the rest of it, but then I was looking at carbon, I was like, well, where do you get 14 from?
that is a specific isotope. Okay, so let's go and get started. If we're late, we're late. So, okay, so a proton. Proton is what charge again? Positive charge. Okay, so the symbol that you'll often see in the text, it's going to be a lowercase p. Or it'll say P plus. That's going to represent the proton. Okay, now when we start talking about nuclear chemistry, which is the next thing that we're going to be talking about, we're going to make reference to that P as a proton. So it's going to be written like this, but then they're also going to have, that it affects, does it affect the weight or does it affect the?
Oh, it affects the weight because the atomic number and proton.
So we know it's going to affect the weight, and we also know that it plays a part in the atomic number because the number of protons defined. Okay, neutrons. Does neutrons affect the weight? And we know that they're neutrally charged. Okay. Now this tells you who discovered them. Most cases you're not going to use that. You may have a multiple guess question, but they primarily focus on Thomson. Because he's the guy who discovered the electron. A lot of chemistry deals with electrons. Okay, so we know about electrons. Electrons, this is the symbol for electrons, which is E minus. So if you see in an equation where it just says E minus, that means that an electron is. If we see in a chemical equation, let me give you an example. So in a chemical equation, when you see it written like this, So this means that we're gaining an electron. Right? So in this case, we'd be gaining one electron under the circumstance, right? So at the end of the day, this guy would have a negative charge. That would never happen. Right? Or we see something like this. That was lost. So we'll talk about this in a second. It's everybody's. Okay, so when we talk about the atomic number, the symbol that is often used in literature, you'll see is Z. Okay, so we said A equals Z, where A represents the atomic or mass number, Z represents our atomic number, and N represents, our capital N represents the number. So in other words, the mass number is going to equal the number of protons. So, but a lot of times you'll see they'll ask you, and then they want you to know what that means. Okay. We've already talked about how to write the symbol, right? Where that upper number here is mass number. More number is what? Okay. Now, sometimes we'll write it when we talk about isotopes. We'll write the isotope as oxygen dash, and that would be the new mass number. So dash 16. That means that it weighs 16, which is what oxygen is essentially. Right? But if I said oxygen dash 18, that means it's 8. Okay. So remember when I talked to you about the different isotopes of carbon, right? So here's an example. We have 2 isotopes of carbon. We have carbon 12, and this is carbon 13. The difference between the two is what?
The mass.
The mass, which also means the difference is.
The neutrons are different.
How many of you guys say protons? Raise your hand. How many of you guys say electrons? Raise your hand. The difference is neutrons, because we know that protons do what? They're going to say the same. They define that element. That's how we know it's carbon. Okay, so the difference between carbon 12 and carbon 13 is 1 neutron, right? Okay, and we know that its mass is bigger because of that 1 extra neutron. Okay, make sense? Allison? Get it? But do you get it? You know, do you see it, right? 12, 13, the difference between them is 1, right? Protons are exactly the same. Okay, so then the only thing that could change in this case is the neutrons. Okay, so we know what isotopes are. You guys are feeling comfortable with isotopes? Okay, so let's talk a little bit more about isotopes. Before we talk about isotopes, we talked about protons, neutrons, and electrons. Okay, so when we talk about okay, so we know that this was the mass number. This here is the atomic number. This here is going to be the charge associated with the atom. Now, our charge is going to be based upon the number of electrons. Okay, electrons are going to be able to change. Our protons we know can't change. Okay, protons can't change. Okay, protons can't change. Retardant. So this tells me that I have 4 additional electrons because it has a negative charge. Okay, so that means that I have 4 electrons added on. So if I ask you, the number of protons is how much? Yes. Number of electrons. Ten, because we know it has to match up initially. Plus we have 4 more added on. So we have a total of 10. The number of neutrons. Okay. You guys see that?
Yeah.
Not yet.
Yeah, so it's like the opposite, you know, how it's a negative, you're adding.
Yes, you're adding electrons. If it's a positive, that means you're removing electrons.
Oh.
Okay, so let's say, for instance, we have this guy up here. Plus, okay, that means what?
So that means you're taking it away?
So we're taking away what?
Two.
The electrons?
Electrons.
So it'll be
Okay,
4.
so how many protons does this have? Oh, no.
Oh, you gotta go find it yourself.
I do all work for you all
12,
the time.
12.
So we have 12. How many electrons? 10 electrons. And how many?
Yeah, 12.
Okay. Questions? Questions? You'll see it?
Oh, yeah. Well, we see it, we see it.
So normally, if we talked about magnesium weighs how much? 24. Okay. How many protons, or what is the atomic number? So normally magnesium has how many electrons? 12. Okay, and then we know in this case, it's gonna be 12. Because we added 2 plus, that 2 plus means that we're removing electrons. Okay. It means we're removing 2 electrons. Okay. So it has a total charge of +2, right? Okay, are you guys with me?
No, yeah.
Now you know, okay? And that's what is shown up here. So if I have magnesium, I lose my 2 electrons. Electrons being lost.
So if it was minus, you'll add.
Yeah, if it was minus, that means we're adding electrons.
Okay.
Let me give you an example. So if I have F minus, that's not your grade. Okay, F minus means that I have how many electrons? I'm adding 1. So how many does fluorine, how many protons does fluorine normally have?
9. So we 10.
Okay. Okay, and that makes sense because we know that electrons are what charge? Negative, and protons are
Negative.
positive, right? So if I have 9 positive and I have 10 negative, then what's going to be left over? Do the math.
1.
We have 10 negative plus 9 positive. Okay? Okay, so that's how we get that charge up there, that negative, right? Because there's only one of them. Okay, oxygen. Say I have this. What does that mean?
You're adding two.
I'm adding two, what?
Electrons.
Electrons. Okay, so how many electrons does oxygen normally have?
Eight.
And then I'm adding two more.
10.
10 electrons. How many protons?
8.
And then how many neutrons?
So 8.
8.
Yeah.
I hear 2
8.
is 8, right? Because what is the mass?
It's like 16.9, but you would round up to 16.
So 16, right? Okay, you guys got that?
Yeah.
Are you sure? Good. Okay. So now you're going to ask me, why do we need to add electrons? Why do we need to add electrons? And ask me, why do we need to lose electrons? Right? Aren't they happy just being by themselves, being zero, neutral? That's exactly what you're going to ask me, right?
Yes.
Okay, so let me get to that. Take a moment to go to the periodic table. So now I talked to you guys about it, and we didn't talk too much about it. Briefly discussed it. But we talked about the noble gases. Right? These guys here, these are the noble gases. Okay. Now the noble gases are like the cool kids, like noble, right? They're kind of rich. She has a term, that kind of talks about that. They're like the rich kids. Everybody wants to be like, you know, you heard of the Johnsons. Everybody wants to be like the Johnsons, right? Because they have everything they don't want for nothing. Everybody wants to be like the noble gases. Everybody else is lacking, right? They're not rich. They're trying to make it, right? And so there's a couple of ways that you can make it as a chemical, right? Or as an element. One way is that you can take, right? You take it from somebody. Right? Take an electron from somebody to be like a noble gas. Or you can give up electrons. Oh, I'm going to give you some electrons. Give them away to you, right? Okay. So some of them are going to take, some of them are going to give. Okay. Or you can share, right? Get together, make a couple, you know, and share. Okay. Now, when you're taking and giving, that's called ionic, right? This is called an ion. Ion is taking and giving electrons. Okay. So if it's a positive charge ion, it's called a cation. Cat ion. Everybody wants to say cation, right? Cation. It's not cation, it's a cat ion. That's positive. Positive. Cat ion. Okay, so if it's positively charged, it's a cat ion. A negative ion is called an ion. AN ion. That's a negative ion. Like a negative, AN ion. Okay, so positive ion is called and a negative ion, anion. Okay, now the thing about cations and anions, what they'll do, they'll come together and they'll form a neutrally charged compound, right? But they're happy because they're happiest when they're like their charged parts, right? They got that charge, but they're also very happy when they come together. So for instance, we have sodium chloride. Na. Okay, sodium chloride. So sodium, if you guys look at where sodium is located right here, right? Now sodium has the ability, it wants to be like a noble gas. So it has ability of trying to gain 1, 2, 3, 4, 5, 6, 7 electrons to be like argon, or it could lose 1 electron to be like neon. Okay. Now, if you think about it, like you had the option of going to a store. Same store. One is a block away and one is 7 blocks away. Which one are you gonna do?
7 blocks.
You're gonna go 7 blocks?
I'm going to the one right around.
Okay, gas me what it is. You're gonna drive that 7 blocks, or are you just gonna go across? You know, I'm gonna walk right next door and go to the one, because guess what? One thing, we're lazy, right? We don't wanna spend money on gas, right? And so you're like, man, I gotta cook this meal.
But they don't have to.
Yeah.
Yeah.
You're gonna go that one block, right? So just think about you, and be realistic, you're not gonna, it's right here, or you're gonna go across town, you're like, hell yeah, I'm gonna go to the one that's right next door to me, right? Doesn't make sense to go to the one across town, if they have exactly the same thing, right? Okay, so think about it like that, and that's what's happening here. You're gonna try to do the thing that's the least amount of energy. These elements are gonna do the things that are the least amount of energy. It's more energetically favorable to be like a noble gas. So in this case, you want to lose that electron so that you can be like a noble gas. So sodium is going to lose one electron. So if it loses one electron, what's going to be the charge on sodium? What was it?
If it loses one, you said?
Positive. If it loses one, it's going to be positive. So we're going to put plus. So guess what chlorine is going to do, right? It's going to be like, huh, you're losing that electron. Guess what I'm going to do?
Gain it, right? So it would be negative.
That's right. Chlorine is right here. It wants to gain, right? So it's going to take that electron. Now, what do we know about positive and negative?
They attract.
They attract. So then they're going to come together and they're going to form sodium chloride with no charge because they're both, that's right, they cancel each other out, right? They're happy, right? Opposites attract, right? I can change him, remember that? Okay.
Not all the
Okay.
time.
Yeah, we'll talk about that here in a second. right? Okay, so this is an example of those ions coming together to form an ionic compound. Okay, this is called an ionic bond. Yeah. But these are just the ions. Does that make sense?
Overall, like sodium.
Yeah, sodium is like, because sodium is very volatile. It's a metal, right? This is metal. If I put it on the table here, it'll actually catch on fire because it'll start reacting with the atmosphere, with the water. It'll like, believe me, I cut a slice here and we have to coat it in oil. And as soon as you wipe the oil out, it starts to react, right? And I called myself, I was doing the experiment and I should have measured it. I was trying to be in a hurry. I was doing it as an online demonstration, teaching class online. And hit my slice, I wiped it off, and then I turned my back for a minute. Next thing you know, whoosh, it just blew up, and it knocked the computer off the table. I had dust. I mean, it was everywhere, right? My ears were ringing like for 4 days because it was so loud. It was just that bit of sodium. Now, sodium is very, very reactive. These metals here are very, very reactive because they're so anxious to be like a noble gas. They're like, fuck, I want to get rid of that one electron so I can be stable. I can have a normal life. Happy, right? So they're just like anxious about it. That's the same thing over here. The halogens. The halogens, that's the reason why we have a special container for the halogens, right? Halogenated waste, non-halogenated waste. Because those motherfuckers, they get crazy too. They're like, I'm one away. Right? I will rip it off from you. I take it from your eyes. I take it from anywhere, right? I will take that electron. I'm getting it some way or another. You're going to give it up, right? One way or another, you're giving it up, right? And so they're going to be very, very volatile, right? Crazy people, right? So we think that they're very volatile. Those reactions are insane, the things that happen, right? So if we had fluorine, they're all gases over there, except for acetylene. Acetylene and iodine, both are not gases, they're salts. They react like crazy. I mean, they do. They all do react like crazy. You get them out here, they react. They're anxious to react. Right? Iodine is sublime, so it takes a moment, but once it starts reacting, you're like, fuck. So it'll literally go from a solid to a gas. Once it gets to that gas state, it is anxious. Things are gonna start happening. So we do an experiment in 1A. It is really cool. I always catch the students off guard because it's one of those loud experiments, and then you get this burning thing that happens at the same time. it scares the shit out of them, right? I love it because they're like, oh, we're ready to do an experiment. And none of them read the lab like they're supposed to, right? As soon as they don't read the lab, I'm like, okay, take advantage of it. I just give them bare bones. They get in there, and then the next thing they know, shit starts popping and they're all jumping around and everything. So you got to get to my 1A classes. Anyway, so and that just plays on the fact that those atoms are very they're anxious to try to get stable. And that's kind of like us, right? You know, the reason why you guys are here. Are any of you guys here because I just want the prestige of going to school? Any of us do that? Right? No, we're here because we want to make more money, right? We want stability, right? So it's that concept of if you have that ability, if you can marry into wealth, you marry into wealth, right?
Sure would.
If you can sit there and get your education and earn $1 million on your own, get your education and earn $1 million on your own, right? So we're trying to find a way to find stability, right? And that's the thing that is happening here. And it all boils down to energy, right? Energy level. You want to try to use the least amount of energy as possible. You want to find the easiest way to get to where we want to be, right? And we look at it as if I get my education, that gives me some form of stability. Or if I marry Jojo, who's a millionaire, then that gives me a form of stability, right? So, okay, so yes, only those are noble guesses. So group 18, you guys remember up here? These are what numbers? These represent what? The groups, and these represent periods. That's right. So these guys represent the periods. This represents the groups. Group 18 are noble gases. So those guys, they don't really like to react. They will occasionally, right? And the only time that they react is when something else forces them to react. Because most of the time they're just like this. Let me show you something. Let's see if I can do this for that. Hold on. Did I already show this to you guys? Okay, I'm gonna ask you a question. Now you should be able to answer it since you're talking there, right? Okay, you ready?
You asking me?
I'm asking you. Yeah, I'm talking to you. I'm hearing all the gossip about shit,
I'll do my best. I'm listening.
Okay. Okay. So we know what about the noble gases?
The noble gases,
Mhm.
they are in the group period 18.
They're period 18, are you sure? No, put money up. Put $5 on the table. I got $5 on the wall right now.
Well, noble gases is.
Come on, money talks. Put the money on the table. Put the money on the table. Believe in yourself. I got $5 on the wall. You sure?
I'll put $5 on the
Are you sure?
So can I get my $5?
No, you can put the money on the table. You put the money on the table.
I ain't got no cash. I got cash app.
You got the cash app?
Yes, I
Okay.
need
Next time we'll send cash app. You'll send it. We'll put it in a pot. We'll see. Okay.
Next question.
Next time. 20 on the table. Are you sure? Okay, I like that. Let's increase those odds. Okay. Let me see. Okay.
Wait, was that right though, for real?
It was groups. That's right. Group 18. Not periods, what you said at first. Hold on. Give me 1 second.
You know, all the blues, yeah, all about everything, all about that. But it was like all about the acid. It was known, but it was like all acid. I don't know. This is something about acid. I was always like on the three groups interesting about acid. Well, you know how they do it in gym, like, what was the other one?
Can't get it now. I can't get it now, but I can get it. Can't get it now. I can't get it now, but I can get it. Walked up the stairs. Walked up the stairs. Can't get it now. I can't get it now. I can't get it now, 'cause the bucket downstairs are going to quit. The bucket's downstairs and they quit. I can't get it now, I can't get it. I can't get it now, but I can get it. Can't get it now. Can't get it now, but I can get it. Can't get it now, but I can get it. I walked up two flights. Walked up two flights.
Okay. So. Try now. Is that better? Okay. Okay, so what was it that you guys saw about this noble gases? Noble gases.
They don't bond with each other.
The carbon bonds a lot. Noble gases, what about the noble gases?
Do not bond.
They do not bond.
They do not bond, right? Right, Joey?
Yeah.
I want the paper towel. And I have it down, I have it like this.
Okay. So you guys decided to look at the lecture. Half the lecture won't have any volume at all. Because apparently didn't turn it up. Half the lecture will. So anybody who missed that first part of the lecture. Anyway, so we know that the noble gases aren't going to want to react, right? Because they're stable. They're already stable, right? Now, if you're good, you're like, oh, you're good, you got everything you want, or everything like that. You don't want for anything. You're good to go, right? But everybody else needs to try to get somewhere. So typically what happens is that, like I said, you're going to either take, you're going to give, or you're going to share. Okay. Now, the reason that you would share is that if you're on the same side, right? So all of the these are called non-metals, right? If you guys take a look up here, we have non-metals. So these are all non-metals. These guys are noble gases. These guys are going to be the ones that are going to be reactive, meaning they're going to want to react. They want to try to get like the noble gases. So if these guys come together, they're going to be sharing electrons. Okay. Now, if you're a non-metal that's reactive, you're going to want to react with a metal because then you can take electrons. If you're over here, you're going to share. That kind of makes sense, right? So, like for instance, let's say you're a thief. I'm not saying anybody's here is a thief, but if you were a thief, right? Now, would you steal from your neighbor? Your neighbor has this brand new motorcycle, it's a badass motorcycle, right? And there's a guy, you know, in Huron, right, who has the same badass motorcycle. Would you take the one from your neighbor, or would you take the one from the guy from Huron?
Yeah.
Why?
It's farther away.
Because he's further away, right? So it's kind of like here, right? Non-metals are going to react with our metals because they're kind of further away.
And what's that called again?
What kind of
When-
bond is that?
It's an ionic bond, right? Because that's going to be taking and giving, right? They're going to be taking electrons. The other ones are going to be giving. So the metals are going to give up electrons. The non-metals are going to be taking the electrons. Okay. So these guys are going to want to take electrons. Now, if you have two non-metals, they're going to share electrons. Now, sharing can be even or it can be uneven. Okay, even sharing, right? We call even sharing non-polar bonding, right? Uneven sharing we call polar. How many of you guys have siblings? Everybody got brothers and sisters? Are you guys the oldest and youngest?
You said, I'm
Oldest.
sorry, even share is what?
Even sharing is called non-polar, yes, and uneven sharing is called polar. Okay. The reason why we call it polar is because you form pole. One's going to be a positive pole, one's going to be a negative pole. It's uneven, right? If it's even, then you're both kind of neutral. Okay. So this here is an example of an ionic bond. Because it forms an ion, it's positive and negative. Barn is an example of a polar. Call it a covalent bond. Positive and share. Okay. Now, let me explain to you kind of what's going on in the case of water, right? So hydrogen is a non-metal. It's going to be reacting with oxygen, and they're going to be sharing electrons. So when they share electrons, and I said, how many of you guys had siblings? You said older? You guys were older? Okay,
Younger.
so I'm also older. Who's younger? You're younger? Okay, so you can kind of appreciate this, right? So I'm the oldest of my siblings, right? I have two younger sisters. So when we were growing up, we had to share. Like we need a lot of things for Christmas, underwear, and we get one big gift, right? And that one big gift, like one time we got an Atari. You guys don't know what an Atari is. I understand this. It's the equivalent of a PlayStation, right? I know you guys get that for yourselves, independent. Like your families are rolling in dough. My family was poor. We were living from paycheck to paycheck, right? Every paycheck it was tight. So when you got a Christmas gift, you really appreciate that Christmas. So my mom says, okay, got an Atari for Christmas. You guys got to share it, right? So, get Atari one down. You know, I'm like, well, you go in my room. No, can't go in your room. Goes in the living room, right? I didn't have a TV in my room, but I wanted a TV in my room too, right? So goes in the living room. We had to share it. My parents worked. My mom had two jobs. My dad was on the boat. He was in the military. And so when he wasn't on the boat, he was also working another job. Again, he did it. And literally, my mom says, okay, you have to watch because she worked two jobs. I had to watch my sisters. So the way it worked was I get up in the morning, I play video games. I was responsible for cooking and cleaning and all that stuff, right? So I did all the cooking and cleaning, make sure my sisters did their fair share of it. Well, they didn't really cook if they didn't know that. That's what we did. Well, I mean, not going to. I did most of the cooking. I learned to cook. My sisters, she struggled to cook for a long time. She could cook fried chicken, and that's about it. My other sisters, meals, no meals. She can cook cakes and cookies. That's where we want to go for the cakes and cookies. But everything else, I could get on. Okay. So the deal was that when my mom got off initially at 3 o'clock, roughly around 3. So what would happen is like in the summer, I played a video game up to like 2:30, and then I started cooking and cleaning, get everything done. My sisters did all the cleaning, and then I did cooking. And then while I was in there cooking, I let my sisters play the video game, right? So that 30 minutes, and my mom would come in 30 minutes, I'd still be cooking, right? So they get to play the video game for about an hour, right? Now I played it all morning and in the afternoon, right? And they got to play it for about an hour and a half. And then afterwards, I'm like, okay, it's my turn. And I play the rest of the night, right? So we were sharing. Was that fair? Is it even sharing?
No.
It's not even sharing, but was it sharing?
Yeah.
Right? It's sharing, okay? So I did what my mom told me to do, right? I shared like I was told to do. Now, nobody said it had to be even sharing, right? Now, it's one of the first being oldest, right? So what happens in the case of hydrogen and oxygen is they share electrons. This line here represents the electrons that are shared between the two. Okay. Now, what happens is that oxygen is stronger, right? It's the older brother. Since it's stronger, it's going to be pulling electrons towards it more. So in other words, oxygen is going to have the electrons more to its side than hydrogen is. So then it forms what we call a pole. Partially positive. This guy's going to be partially negative. Where in the case of this guy is all negative. All positive. All positive, and this guy is all negative. These guys are partial because the electron is moving from those two, it's moving between the two, but it's spending more time around oxygen. Let's get that. So since the electron is spending more time around oxygen, it's going to have that partial negative associated. So it's going to form a pole, not a complete negative, partial. Where this chlorine ion is completely negative. Okay? Are you guys with me? Okay, so these guys form covalent bonds when they bond together. Right? But when they bond with a metal, a non-metal with a metal, it forms an ionic bond. Somebody has to give up something. Right? So that means that the metal gives up its electrons to the non-metal because the non-metals are going to be stronger. They're going to take it. That money, take your money, right? That's the way it's going to be. Right? So ionic is going to be give and take. Somebody's going to be giving it up. Somebody's going to be taking it. Covalent is going to be sharing. Okay. So, and they do this again. Why? Why do they do this? Guillermo, why do they do this? Well, one stronger than the other, give me more details. Why? What is the purpose of it? Why the hell are you in this class? To get more money, to get stability. So why do you think they're doing it? What are they getting from it? Stability, right? They want more stability. So they react to become stable. So you get a reaction to become stable. So your noble gas, you have everything. Do you need to react? If you have everything you need in life, would you be? Right? Right? Okay, so noble gases don't need to react, right? Now, if your buddy there needs help and everything like that, you may help your buddy, right? So the noble gases, what they'll do, they'll occasionally help some of the others because you're so trifling. Let me help you out, right? You guys know those people that you gotta just fucking up. Get your ass, come on, let's go, right?
Me, I'm the effort.
So then you drag them along, right? Okay. So that's what happens with the noble gas. The noble gas don't want to do anything. They're like, we're good to go. But everybody else wants to be like the noble gases. They need that stability. Okay. Now that's what this all deals with, right? So that's where you're going to be giving or taking electrons. That's what a chemical reaction is. It's trying to get to the part that you're stable. Okay, and we use it to our advantage, right? How many guys clean with it? It tries to get stable, right? So it forms initially it's stable, it smells a little bit, it's kind of stable. As soon as you put it in water or something, those ions separate, they start doing crazy stuff because they're trying to get back to that stability, right? That's part of that cleaning action. So we take advantage of those type of reactions. And there's always grass is greener on the other side, right? You guys heard of that? Grass is greener on the other side. Where you're with somebody and you're like, they're good,
Oh,
or
that's
anything
our
like that.
relationship.
And then you find somebody who's cuter or better, you're like, something here, you know, and get to the next one, right? So it's just like those relationships,
Are you
right?
a psychic? I'm just kidding.
On the side, you know? Okay, so do you guys kind of get this? You see how it works? And it's important. If you guys think of it like that, chemistry is fucking easy because it's like real life, right?
It makes sense when you're talking like this.
Yeah, it makes perfect sense because that's the way it is. It really is. And the elements are very much like us. They're trying to find ways of finding stability, right? So we get, why do we couple up? Why do you get with your boyfriend?
To create that
A lot of reasons, right? But one of the reasons is stability, right? We looked at it as, oh, he's a good man. He's cute. She went through his list. He meets these requirements, right? Yeah. And then you're like, okay, that works, right?
No.
Now,
No.
your ex, or your ex, right? They were like, they're exes for a reason, right? Because they didn't meet those requirements. So you're like, okay, I'm moving up. I'm not moving down. I'm moving,
I need to know the gas.
yeah. You pay the bills, do what you're supposed to do, right? So that's why he was kicked to the curb, right? So,
I need to know the gas. I know, I didn't know the gas went wrong with that person.
Double bond,
so they are not.
double bond.
So you mean to tell me noble gases don't bond with nobody?
No, they only do it when they have to, or when they're trying to help somebody out, right?
Okay.
So, but that's the only time that they do it. They're like I said, they feel sorry for you.
Oh.
You're a hot mess. Let me help you out. Right? That is the only time that they do it.
I love this. I needed this. I needed this class session today.
Okay. And then we have Bailey.
Unless they're trying to help somebody out. So. This is about to turn into Dr. Phil.
Maybe, that might be.
I gotta go back. So this last part of the lecture is all mine.
Yeah.
All right, I'm gonna go back and reevaluate this class.
Okay.
Lecture was good today. Yeah.
So you guys understand why they're doing what they're doing, okay? So that's the reason why we get those charges that are going to be associated with it is when it's taking and getting. So it has to take it from somewhere, right? Or it has to get it, one or the other. So that's what happens in the case of sodium chloride. And then in this case, this is what's going to be happening to the magnesium. It wants it, and then it does it better when there's stuff around. Now it'll do it, right? And it'll sit there and form those charges and stuff, and like drop that electron, or like hope somebody takes it, and like, because it wants to try to get that stability, but no, it takes it, it's still there, right? Can't get rid of it. So they want somebody to take it, they can't. Everybody got this down so far?
Not made of glass.
What was that?
Not made of glass.
What was that?
I said you're not made of glass.
Oh. What do you mean? That is glass made.
Oh,
Is that better?
yeah. He always knows.
I like the. But I really like.
Okay.
See, this would be just.
Okay, so let's see what we can do. Now. Back to it. Here on the table. Okay, so we have a periodic table, right? Now, so we've talked about metals. All of these guys here are metals. These guys here, these are called metalloids. Now, metalloids, they have characteristics of metals and non-metals. Okay, so they kind of like play that field. Oh, I'm kind of like a metal. Oh, kind of like a non-metal. So depending on who they're interacting with, they're going to behave differently. Okay, these guys are called transitional metals. Now, transitional metals, they're like the hot messes of metals, right? They're just like hot mess. Transition basically means change, right? So instead of having a normal set charge that's going to be associated with them, they're able to change their charge. Part of the reasons why they're hot messes. So depending on how you interact with them, like temperature you put them at, who you put them with, they can have a +2 charge, they can have a +1 charge, they can have a +6 charge. So it just depends, okay? Now that's all of these guys. So these guys get a little more complicated. So we kind of like saving this to last and actually in some cases, they don't even talk about it. But you guys are going to talk a little bit about transitional metals, particularly when we talk about naming. Okay. Group 1 metals. Group 1, or you can call group 1 metals.
That's the number on top, or-
Because it's group 1, right? Okay, group 1 metals are also called alkali metals. These are the ones that are going to be very reactive, alkali, right? They kind of sound like they're reactive, right? Group 2 metals are alkaline metals, right? These guys are less reactive. Alkaline, well, sounds like softer than alkali, right? Like some RT alkali, right? Alkaline metals are going to be reactive, but they're a whole lot less reactive than group 1 metals. Group 1 metals only need 1 electron to be like a noble gas, or get rid of 1 electron, not get rid of 1 electron. Group 2 metals wants to get rid of 2 electrons to be like a noble gas. Okay, so these guys are always going to have a +2 charge when they form ions. These guys are always going to have a +1 charge when they form ions. +2, +1. Okay.
So when you jump to the other side, the other non-metals, we start with the halogens, what is that, -3 or is that 3?
How far away from the noble gases are they? Where's the noble
What about the
gas?
charge? So it's
I know,
2.
but where's the noble gas? Because again, you want to try to be like a noble gas, right?
So it's -2.
How far is it away?
It is 1.
It's 1 away. So then
It's
if you get, it's 1, so it's going to have a -1. So then what would we expect oxygen to be?
-2.
-2, because it's 2 of them. What about nitrogen?
That's 0, right? 3.
It would be -3. That's right. It's 3 away. Carbon is kind of in a special case because if you look at carbon, it goes 1, 2, 3, 4, right? It can go 4 this way, but it can also lose 4. 1, 2, 3, 4, right? So carbon, again, remember we talked about carbon being a whore? Right? Right? Part of the reason why carbon is a whore is because it's right there in the middle. It's like, do you want something? Right? Do you need an electron? I can hook you up. Baby, I can take care of you, right? Or you want to give me an electron? I can take care of you, right? So carbon can kind of go either way depending on the circumstances. So it could go +4 or it could go -4, right? If it needs to, right? So carbon is looking out for you, right? So, okay, so that's one of the reasons why carbon is that special case. Now, silicone kind of works exactly the same way, but silicone is a special case. What is special about silicone compared to carbon? Look at that color. It's a metalloid, right? It's a metalloid. So it's even more of a special case, right? It can go 4 either way, right? It definitely will swing both ways, right? And so they kind of believe that silicone could be the basis of life for certain things as well, too, right? We know that for us, carbon is our basis of life. Everything that is living is carbon-based, right? Okay, so let's talk about this now. We talked about isotopes, we're going to talk a little bit more about isotopes. So let's say I have okay. So how many protons? How many electrons? How many neutrons?
7.
Okay, piece of cake. What will be the atomic mass of this compound? Okay. And its atomic number? Okay, you guys ready for a competition?
What is it?
Atomic number? I'll put it up there. Everybody has their periodic table, right?
Oh, no, don't do it.
You want me to do it?
Yeah, like second.
Okay, guys, ready? Ready, go. Same competition, we'll just have some points, right? We'll do it like this. So it'll be 3, 2, and 1. First group, they get this, right? They in first, we'll get 3 points. Second group will get 2 points. Third group will get 1 point.
Is it gonna be like the one that's with carbon?
Huh?
Is it
It's
gonna be
gonna-
like the, like that?
Oh, it's gonna be, well, yeah, it's gonna be sort of like that. Let me take a look at it.
Oh,
Take it, take a look at it. Got to take.
What is the last section say?
It says ion isotope. Ion. 13 go. That's it. You want me to put- I can put another sheet up there.
No. I just didn't know when you get going and go.
Oh, this would be. Yeah.
The last one.
The second one.
Like that.
It's over there.
Yeah.
No, that's for the person.
So. I know we probably, I forgot, but the atomic mass and mass are the same thing?
The atomic mass.
The mass.
Yes, the only thing was a whole number.
It's rounded.
So that before number what's.
Yeah.
They're saying mass.
Yeah.
They're the same thing, only one has the whole number, and one doesn't have. One rounded, one.
For 201.
But HU, no, because it's 5, so. Yeah, so it's. So it's HU.
Oh, that's what it is. I'm confused because we always learn that 5 and up is round up. But that's how the 6 fix though. I don't know.
But regardless, it's still HU.
Go ahead and mark it up.
Yeah, so we can figure it out. Yeah.
So the closest one would be like. Or what? I think it's MD. For times 6. Yeah, that's 41. It should have been like 7.
That's all right. But that goes.
Because you know, I was just requesting all the massive changes.
Already given. I was already given. I should look at it. has to be 79. Oh, but I didn't know that. They got the wrong numbers. It's not adding up. Oh, I remember. Yeah.
Yeah.
Oh, wait.
That's the plug. It's 52 plus 41.
What's that?
Yeah, I thought it was,
So,
yeah, so how it's, I thought you added it. It's 92.96 would be 93.
Okay, hold on.
Wait, no, because
That's what happened.
technically the zero can round like the 9. So you keep it as 92, right? It's rounding off the next number. It's rounding off the 2.
So technically it's rounding up.
So it'd be 90.
We added it.
Okay, yeah. Other than that, we got the rest. How is it supposed to though?
No, I
Yeah.
sorry.
I said both.
Yeah.
Peek everything. Oh, shit. Like, I do it.
No. So that's not- Yeah, no, I did just to see it, but it is a. So I am all the electrons. Right?
Yeah.
I take the one. I'm gonna write that out.
It's the 5 that goes up to the next number, right?
It said AG.
No, this is. Yeah.
So we're not different.
Yeah, I'm gonna go.
Everything else, we have different. We have the same. Those we have the same.
We only have one.
And those we have.
Oh, no, what did it be? Oh, you.
Think about some.
All good.
I thought.
So these are right. We have all these ones. These are gonna be wrong.
Do you want to show?
What is right here?
You're wrong. You're wrong. I'm not sure. No, because that, that's right. That's wrong. That's wrong. That's wrong.
I didn't catch that.
The bigger one's wrong there, and then the atomic mass. So should we take it and see? Which one? It's gonna be the same.
Like they're around. No, 92. Wait, what? How'd you go on 21?
That's what.
Where does that come? Oh.
My bad.
I thought it was the last one.
So all you.
Yeah.
Let's not worry about that. Yeah, let's worry about this. See, no.
For the first one for MD, the atomic mass.
Oh, 126. Oh, you. Yeah. You gotta look at there, so that means the math changes. I don't know how the math changes.
So then the mass will be. Right, go up. And take it up to the letter circle where it's wrong.
Okay, just one goes over there. Yeah.
Oh,
Take away electron.
yeah, right? But
And add electron.
I thought you couldn't.
And take away photon.
That's what I was thinking. That's what I was thinking. Because she's saying that it's Hg for gold, but I'm, no, Hg for mercury, but I'm like, no, it has to be gold.
That's what it is.
Isn't that given to you?
Photon.
That's so it'd be Au, it wouldn't be Hg.
What you just know?
Because he took away electron.
No, but the photon.
Yeah, but if you can give us the mass and.
But it didn't say anything about it. So that's all I was like, is it wrong? Like, it's on the sixth. Like, oh, it was, or it was wrong.
No, it's not Hg. It's Au.
Always the same. Actually occurs.
Okay.
Yeah. Do you want
Kill yourself.
That's what doesn't make sense. The atomic number is the proton. I see what you're saying, Joel, about the last one. So basically,
Okay.
So let's try this way and we'll throw it.
I mean,
Did you compare the other?
for which one?
She doesn't work one of each.
Oh.
No.
Only choose what the one. But then look, the match number's not adding up. This is what I wrote down. Yeah. Well, I know. Because I know.
Yeah, because he did see you can't cheat.
Yeah, that's what they say.
Yeah.
But then if the code 70 now, the math doesn't equal. You see what we're trying to say?
So, mass number.
Yeah, I'm on 2 plus 2. So then it's 8.
Because the play that goes.
I see 8 plus.
But it's not equal.
Yeah. But that's what we're trying to like figure out.
So.
What is your fault? We got the isotopes, right?
Okay, so basically, it's the exact same.
I'm disappointed. It was so shady with those roots.
Am I missing?
Got it off with me.
I did, what the hell did I get it? No, that's what you're doing. No, but he's saying,
No, but look, math will be.
Go, come on, let's go.
I want me to go put no fish. No, hold on.
Okay, he said, but they aren't the numbers that are table because those are like something about.
Let me take my phone. That's fine. I don't even put the number down.
Let's go, vamos. I never looked at that.
He said, I'll let me mark it.
He said, you're all set.
There you
No, because I don't like, I thought he was gonna put it like an okay. Like, you're good. I feel so confident.
It's just you added that number, so you added the extra number, the thing, so it changes the atomic mass. Which was explaining that.
Would it be 92? Sure. No, so here's a plus.
For the first. But he would have marked it over there. He would have marked it.
But I think. I put the plus one on mine. No, but did you put 90, did you put 92 on the 99? Wait, no. Six. Why not? Take the thing off. There's a cap on it. There's no cap. Let's say, take that one.
No, not.
My Dollar Tree whiteout actually works in box. So we have to take away break on me.
I have a bunch of, but I did put that was good.
We'll change this. You guys went from over here? On Jake.
That's okay.
She was freaking laughing because wait, so you guys went to the last one? Yeah. Past it. So we were really close. Press that, but I'll cut off. Damn, you guys didn't even post it.
Yeah.
And not on Joe. Yeah. And she's like, oh, she's fine. It's why. I told her my house was gonna get on with it.
That's all I was earlier, I thought it was.
Wait, but then I don't understand. I don't know, I mean,
The math is laughing.
it's really not.
And if it's because the math is
I'm getting this.
It's right down. It says the exact number of electrons and that's their mass.
Okay, so let me give you guys all of it. Okay, so I'm giving you guys a hint. This is your hint. You guys ready? Everybody's ready. Listen, listen. Okay, so when we talk about the mass number, right? We're talking about the mass number the atomic number for that particular isotope, right? So remember when we were talking about her family, she has this big family, right? She has 2 cousins, right? And one of her cousins is 5, and she's 9, right? Okay, now we're only talking about her family, which is 9, right? So the mass of her family would be 9. But if we took the average of all of them together, that's what you get on the periodic table. So you guys remember when she had 5, 5, and 9, right? So 2 of her cousins are 5, right? So those are like your 2 other isotopes. They're both 5. Let's say 5 something, right? Say 6, make it simple, right? So on the periodic table, what we get is it's like so. You get something like this. 90% of it would be 9s, right? 5% of it would be 5, and the other 5% of it is going to be 6. Okay. Now, if you multiply that together, 5% times 6, 5% times 5, and 90% times 9, the majority of the number is going to be close to 9. So it's going to be something like 8.92 or something like that, right? I'm just doing quick averages, okay? So this here represents what you see on the periodic table. That's how you get that 0.92, because it's the addition of all of those masses together, right? Based upon the abundance that's there, okay? So now what you're looking at is a specific isotope. I'm saying that we're only talking about the isotope that's not. We're not talking about the ones that are 5 and 6, okay? Or the one that weighs 5 or 6, okay? Does that help out a little bit? Are you still not at all? Okay, let me give you something very specific, okay? So, and let me go to the direction. He's like, not at all. I'm gonna say something. Okay, so this is neon. This is called a mass spec of neon. So what they determined about neon, this is the isotope. This is one isotope of neon. It weighs 20. Okay, so we call this neon 20. So what is the atomic number for neon? Okay, so this first one weighs 20. So that's how much it weighs, right? And we know that its atomic number is 10, right? So that defines neon. That tells us neon is always going to be neon. It's 10. So now if we look at this, this is what, like 98%. 96, 95, 96. So 95%, 96%. 96 would be thick, okay? And this here is neon 21. Okay, now this one weighs 21. This one weighs 20. And this one is roughly, I'm gonna say, what was that? 2%? Actually, let's make it 1%, because otherwise it won't add up. And then we have, we'll say that one is 3%. We have neon 22. Okay, so now these are the values that we got from the mass spec. These are 3 different isotopes of neon. So in nature, this is what happens in nature. We have 3 isotopes of neon. We have 20, which is the one that is the most abundant. We have a whole bunch of them, right? We have 21, which is only a little bit. We have 22, which is even smaller, okay? So if we wanted to calculate how much of it is on the, what it is on the periodic table takes into consideration all of it, right? It just takes the average, okay? So let me put it in terms of grades, right? Let's say majority of the time you get A's in this class, 99% of the 98% of the time you get A's. But that 1% of the time you get a B, and the other, that 0.001% of the time you get a C, right? Your grade is going to be essentially an A, right? Because the majority of the time you get an A, right? That's exactly what's happening here. The majority of the time you're going to come out with this. So we take the average of this. Our value is going to be, if you guys give me the value on the periodic table.
What?
For neon, how much does neon?
20.18.
20.180. Okay, so that means that it's 20.18. So if we actually did this math, and if we had the exact numbers, its average is gonna add up to this. Okay, so what you guys are looking at, you're looking at only one of the isotopes. You're looking at like this one, or you're looking at that one, right? You're not looking at the periodic table, right? Which is just giving you the average of everything. Does that make sense? A little bit more? Okay, so when you're looking at this one, we're talking about a specific isotope of iron. We're talking about the one that weighs 58. Okay, so it weighs 58. So then what would be its mass, its atomic mass? 58. Okay, because we know it weighs exactly 58. Now you use that 0.0, whatever it is that you get from the periodic table, as if we're talking about all of the iron that's in the world. We're only talking about iron 58. This is a specific isotope. Okay, so then what would be its atomic number? So what would be its number of protons? Because it's exactly the same number. The number of electrons? 23. Why is it 23 and not 26?
What?
Because we lost the
Oh,
electrons, right? So we lost 3 electrons, and where we're at? Okay, now its mass number. So its mass number is just this number up here, right?
I'm sorry, can you press her, you see it on the screen?
Oh, yeah, sure. Okay, the number of neutrons. Okay, and how did you get that? 58 minus 26. Okay, now does that make sense? A little bit more now? Yeah. So the thing is that when we're talking about isotopes, we're talking about a specific isotope, right? This last one here, this one tells us, what are we talking about? All of them, right? So then we're just going to take an average of what we have, right? Okay, this, as soon as you see that point, you're like, oh shit, we're talking about what's on the periodic table. It's talking about all of them. Okay. And so that's when we have to do the rounding and all of that stuff, right? Okay, so does that help?
Yes.
Okay, so you guys should be able to give me the answers, right? Who left there?
That's a.
That's you? Okay. All right, are you saying it's done, it's corrected? Oh, it is corrected? You got this, all the stuff you needed from there?
I'm hoping they're.
Okay. We'll see.
Bottom one. It's the bottom one.
It's the bottom one?
Don't say that.
I see what you're saying. It's the bottom, you're talking about the first one.
Yeah, it's on the bottom.
Okay, I need you guys to.
Yeah.
You got it right?
And it's because I didn't mark it up at the top. Just one. Just one. Okay.
It's not 120.
She saw that we got her watch like
Okay. Still this one. Protons. The number of neutrons, right? So you do that math for me. Yep.
Oh, shit.
I'm so sorry. Very long.
Okay.
What type of what?
That's what that's what they do. I went on.
Would you bring here?
We're close.
Yeah, I do work here still. I'm gonna be right at one of these.
So tell me, is it an ion? Is that charges associated with it? Is it an isotope? So.
I'm over it.
I'm more than this for sure.
Okay. So tell me, did you guys, was it 4 of you guys or was it 2?
Two. Two of us.
Okay. Let's see. So wait. I want you to help me, right? Help me with my math.
What? Excuse me, I'm sorry.
Help me with my math. I just want to know. Okay, so number of protons plus the number of neutrons should add up to.
No me voy para atrás. Yo no voy a regresar.
No. Now, it should add up, because this is the number of the proton and the number of neutrons.
Oh, that's what we're doing. Sorry, I looked at the wrong side. So what was it?
Number of protons, number of neutrons. Okay, does that?
Wow.
We were all but one.
Wow.
Numbers. Where's this one?
Yeah, this thing.
Okay,
It was
so
1.2.
this
Off by
is
one number.
correct. So
But is it-
now what is the number? But you had it right at first.
I was closer. I don't know if I math.
I'll circle that. And then. You put your number up top.
So who added wrong?
I don't know. I don't think nobody added it down.
No, it's Jason said 118.
What's it?
It's okay.
I haven't. I don't know.
Okay, so that is correct, that is correct.
I wanted to do because I feel like
And
might be kind of a big jump.
No, 79 is okay.
Going home, doing homework, then going to work. I didn't come from. I don't know who the
Now, remember, if it has a charge and it has these
Where
guys
you
over here,
going?
No.
it's gonna be flipped.
Bruh.
The way that we do
Ions,
it.
Yeah.
and
So one, two,
it has a charge also.
Or one of the
Charges.
This is real.
This is- see, that charges.
Wait, what's it about that?
Go. She's an argument.
122. Are you sure? You guys get plus one. Okay, tell me everybody who's in your group so that I can you guys. Okay, just write it on a piece of paper. You guys, how you guys doing? Everybody Did everybody get this? You understand it?
Now.
Understood it. Now? So do you guys like competition?
Right.
Well, you guys love it because you guys have fun.
No.
Yeah, let's say
That's good.
I've listened to the word that came out of your mouth.
Okay, so tomorrow we're gonna start here, and then those, we will be doing the other lap, but we're gonna start when we finish this chapter, and it's gonna be real quick, and we're gonna go over, because we've gone over most of it. And then we're gonna touch on chapter 20. It's not all of chapter 20, I'm gonna give you the major points.
The Z.
Major points of chapter 20. Okay. Okay, and it's still real.
You're a lot closer. Okay, wait. QU.
I have it right.
Okay. So we'll
Hey,
be
we
here
have to
first,
bring for those.
and then at the, when you guys.
Write it. I see what you did. Always get effort in the letter.
What was that? No points for effort, no. It's real life, real life. You get points for effort for real life? No, you get the job and you don't, right?
Can you see it?
Okay, so who's always?
Plus 10.
Every time I think like 10.
Oh, you want plus 10?
Yeah.
It's nice to want, right?
No, we also helped the other group and the last one.
Oh, you helped the other group?
Yeah,
Yeah.
well, basically, I was like the one that called it out, but they